Hello, good morning everyone. My name is Pawan Kumar. Our paper title is Efficient Data Reconstruction in Sensor Networks Using Optimal Locally Recoverable Codes. This is a joint work with my guide Dr. R. Selvakumar. We are from VIT University Vellore, Tamil Nadu, India. My presentation outline is as follows. Introduction. Then briefly we will see what is distributed erasure codes, locality in coding theory. Then based on that we will propose our system model. Then evaluation of the proposed model, conclusions, and followed by the references. So wireless sensor networks are employed in a variety of applications ranging from sensing to the control systems. The fact that sensors have the capability to operate in diverse environmental conditions where human intervention is almost or nearly impossible. So this motivates the fact to explore and develop new algorithms and designs for increasing efficiency of such sensor systems. Sensors deployed in a large geographical area to monitor will continuously transfer the sensed information to the base station or the gateway node. Typically, the sensors will gather information such as humidity, temperature, and other vital parameters. So, in a typical pull or query based information gathering sensor system, a query will be injected in the sensor network from any of the sensor nodes randomly, and all the other sensors in the network will transmit or forward their data to the node from where the query has been injected. It will create huge latency in case of the large sensor networks. As a consequence of high traffic to a single data node or that is called as a data collector node, a network hotspot will be created. And also another possibility is the data sensed may also be lost before transmitting it to the data collector or sync node due to the network disruption or congestion or the failure of the network node itself. So, data loss, which happens during such scenarios, may also prove to be fatal in mission critical applications such as vehicular ad hoc networks, rescue operations, control systems, etc. And also, sensor nodes with limited memory will not be able to store all the sensor data, which in turn has to be sent to the data collector during the network availability. Like the sensor networks nodes will have the limited capacity to store the data, whichever it senses. So if the memory capacity is exceeded, then the data will be lost. So to overcome this issue, erasure coding can be efficiently used for reliable storage and dissemination of the information. The construction of message M from any key out of the n packets received is briefly what is called as the erasure coding. So we'll see briefly what is decentralized erasure coding. So decentralized erasure coding in the wireless sensor network setup was proposed by Demarcus et al. Initially. So distributed erasure coding problem in wireless sensor networks refers to querying any k nodes out of the n nodes in the network and obtaining sufficient information to reconstruct the original message from any k nodes. The number of k nodes are not fixed. It can be anywhere on the network out of the n nodes. So mathematically, a data packet Pj sensed from the node Ki is forwarded to Nj storage nodes randomly. At the storage nodes, the received packets will be multiplied with an element from the Galois field and it will be encoded. This encoding is similar to the forward error correction where the message or the data will be multiplied with the generator matrix and the encoding is performed. And getting the actual packet from the encoded message or the encoded packets is similar to solving a system of linear equations to solve for P knowing E and G. Now we will briefly see what is the locality in coding theory. Locality refers to the number of nodes required or accessed to correct or reconstruct the messages in case of a node failure or faulty nodes in terms of the locality. The codes with the small recurring sets are attractive in case of wireless sensor networks where energy and communication trade-offs are of major concern. So this is the decentralized erasure coding scenario. A code C, which is a subset of field F over the alphabet Q of size n is said to have locality R if every symbol of the code word X in the code word space C can be recovered from a subset R other symbols of the X. Such codes are represented with parameters n, k, and r, where n is the length of the code word, k is the information or the message, r is the locality. The rate and the minimum distance d of such codes are given as follows. The codes that meets these bounds with equality are called as optimal locally recoverable codes, and these codes are proposed by Tamo and Barg. So our contribution in this work is we are using the optimal locally recoverable codes proposed by the Tamo and Bar, and it is tailored into the domain of the wireless sensor networks, similar to the decentralized erasure codes. The proposed scheme demonstrates that if a node fails in the sensor networks, it is just sufficient to access other nodes in the partitions to reconstruct the message. And also we can see that the latency reduction improves the performance in terms of the IO cycles required to reconstruct the lost packets. So this is the system model. So decentralized erasure codes from optimal locally recoverable codes is achieved as follows. Let Bi as a subset of Ai of size R, and Bi is equal to for which where beta I1 to beta IR, where I varies from 1 to k by R. In systematic encoding, message symbols are written in coordinates locations in sets Bi. For each set Bi, define R polynomials pi ij with j varying from 1 to R of degree less than R such that pi of ij of beta of jl is equal to delta of jl. For k information symbols, A, which is given by aij with ai varying from 1 to k by r and j from 1 to r, the encoding polynomial is given by fa of x, where fi of x is given by this term. The polynomials fi are the linear combinations of the polynomial 1 to g with j varying from 1 to k by r minus 1 and satisfies the conditions that f dash of aj is equal to delta ij for all j varying from 1 to k by r. Thus formed matrix V is an invertible van der Monde matrix, and this ensures that the code is systematic. Any properly chosen submatrix of such van der Monde matrix is invertible, and such property is helpful in designing distributed erasure code kind of setting from systematic optimal locally recoverable codes in sensor networks. So this ensures that querying any k nodes out of n nodes will yield the information or message sensed from sensor nodes stored at different distributed nodes. So in our work, we are concentrating only on the failure nodes. So if I suppose a node which is acting as a decentralized erasure code, if suppose a node fails, then like instead of accessing all the other nodes in the network, we can just access the recovering set and we can get the information at that particular node. So this is the, like suppose a message M censored from the sensor nodes will be routed uniformly at random to n storage nodes. Each storage nodes will have the coefficient Gij chosen from the Galois field, and the message will be encoded as follows. So message M, which is censored from the sensors, will be multiplied from the element of the Galois field, and it is encoded as C1 to Cn and stored distributedly in the network. Similarly, decoding is performed by properly selecting k columns from the matrix that are invertible. Decoding will be successful only if the selected k cross k submatrix is invertible and form a system of linear equations. Message M obtained as follows by decoding. So it is given by, and the major condition is this matrix G is invertible. By using the distributed erasure code setup constructed from the systematic optimal locally recoverable codes, it is enough to access R nodes in the partition rather than accessing K nodes of network to reconstruct the lost information at the faulty node. So for evaluating the proposed model, like we are implemented this in the MATLAB running on HP Z220 workstation with Windows XP operating system. And node failure can occur at any part of the network, and reconstruction of such failed nodes is done by accessing other nodes equal to the locality R of the code in the proposed model. For the present implementation, systematic optimal locally recoverable codes with parameters n is equal to 9, k is equal to 4, and r is equal to 2 is considered. Suppose say if any of the node fails, then it is enough to access any other two nodes in that partition. Suppose, whereas in the case of a read Solomon code with similar parameters, then if a node is failed, then any other four nodes has to be accessed to reconstruct the failed node. So we have evaluated with the following two metrics. One is the network load, other is the error count per transmitted packet. So network load, IO cycles per SNR required to construct the message at the last node. So error count is the number of packets received in error to the total number of packets transmitted. It is similar to the bit error rate in case of a physical layer communication. So this is the performance graph. From the graph, we can infer that the network load in terms of the IO cycle required to reconstruct the message is less in case of the optimal LRC, whereas it is higher in case of the typical read Solomon codes. So we have achieved the latency or the network load in terms of IO cycles required is less in the case where optimal locally recoverable codes are used. So this is the error count per sent packet. It's similar to BER, and we can see that using the optimal locally recoverable codes, the error correction is very good, and we can see that there is a coding gain similar to coding gain in case of a BER. So from the simulation, we can infer that the usage of such codes is beneficial in terms of the network load as latency is reduced. And testing the proposed setup in large scale dense clustered wireless sensor networks in order to check the essential parameters such as latency and other quality of service parameters looks interesting. And test the proposed setup with other similar decentralized erasure codes setup modeled in the literature for the wireless sensor networks. To example, some of the models by Alawami and others. It is also interesting to analyze the proposed model in terms of redundancy based event reliability in sensor networks, where only upon occurrence of any event the message will be transmitted to the base node. So, conclusion. So, for usage in wireless sensor networks, we have constructed the model of decentralized erasure codes from the systematic optimal locally recoverable codes. And from the results, we can infer that in comparison to the typical read Solomon codes, the proposed model helps in reducing the IO cycle required in reconstructing the lost message at the nodes. So these are the references which we followed. Yeah, thank you.